Video number 2, we're going to do some confidence intervals now for a difference in two proportions. Now, once upon a time, we used to do confidence intervals for proportions that looked like this. Now everything's basically going to double up, and it's going to look like this. The only thing that truly doesn't get doubled up, in essence, is going to be our z. And to figure out this certain z-score, we had to use inverse norm with our one-tail area. Okay, so if we wanted to find a 95% confidence interval, then that meant we had 5% in the tails, plural, which meant we had 2.5% in one tail. So we would do inverse norm 0.025, and that would give us our z-score. That would tell us how many standard deviations 95% would get us. Okay? Now, everything else is going to come from our problem. To get our p-hats here and to get our n. Those are all going to come from our problems. Now, before we can actually do the calculations, we're still going to do the 3 C's for confidence intervals: conditions, calculations, and conclusion. The conditions are basically all the same as they were before, except now you have to do everything twice, one for each sample. You've got to make sure that your 2 samples are both random samples. Or, here's what might be a new thing involved. The samples may not necessarily be randomly selected, but if you were doing an experiment, you want to make sure that your 2 treatment groups are randomly assigned to the treatment groups. So they may mention, using a coin or some sort of random tool to be able to randomly assign subjects to treatment groups. So they may not say random, that they were randomly assigned, but you need to kind of read into the problem to see how they were assigning people to treatment groups. And if it was involved in some way of using a random generator of some sorts or a random tool, then it's okay. You're still going to have to check if your observations are independent for both samples. So you're going to have to use the population as at least 10 times your sample size in both samples. You're still going to have to check to see if it's approximately normal or not. So you're going to have to do the n times p and the n times 1 minus p, both greater than or equal to 10 for both samples. And it's got to work for all 4 of these for it to work. If it doesn't work, if one of these is not greater than or equal to 10, then all you simply have to say is sampling distribution not normal, confidence interval may not be calculated. And a little side note down here, they may refer to the n times p and n times 1 minus p as successes for n times p and failures for n times 1 minus p. You might see that mentioned in the book for some problems. So I just want to let you know that's what's really going on. And as always, some people still haven't gotten it through their brains, the central limit theorem does not work with proportion problems. So you cannot use it for these problems for proportions. Here's the example we're going to look at. To study the long-term effects of preschool programs for poor children, the High Scope Educational Research Foundation has followed 2 groups of Michigan children since early childhood. One group of 62 attended preschool as 3- and 4-year-olds. This is a sample from population, what we're going to call population 2, poor children who attend preschool. A control group of 61 children from the same area and similar backgrounds represents population 1, poor children with no preschool. One response variable of interest is the need for social services as adults. In the past 10 years, 38 of the preschool sample and 49 of the control sample have needed social services, mainly welfare. So what they're wanting to test here is the idea that if poor children are put into preschool programs, that hopefully that will give them a leg up in the rest of their educational career, and hopefully will result in them being more successful in school, and more successful in school hopefully means a better paying job, which means less of a reliance on governmental assistance like welfare and food stamps. So in our table here, we have our 2 sample sizes. Control group, we said we had 61. Preschool group, 62. Now, you're not going to have to make a table like this for every problem, but it is a nice way to kind of organize your data. Okay? Sample proportions. Out of our 61, we had 49 of them that needed social services later. So that's about a little over 80% of them. Out of our 62, 38 needed social service help, which is a little bit more than 61%. So you can see here we have a 19% difference between our two groups? And is this 19% difference a large difference that we would say, yes, maybe the preschool program does in fact help people later in life in terms of government assistance? So let's compute a 95% confidence interval for the difference between these two groups. So number one, we're going to have to check some conditions. Okay. So number one, the random condition. Are we dealing with random samples or are we dealing with random treatments here? Nowhere in this problem does it mention that these 62 or 61 children are randomly selected. So, and they weren't said that they were, randomly put into preschool or not in preschool. So the main thing we're going to have to write here is sample or samples not known to be random. So proceed with caution. Now, these samples weren't selected from a voluntary response. It's not like these 62 kids volunteered to go to preschool and these 61 kids said, hey, not go to school, sign me up. That sounds like a great time. I want to watch more SpongeBob. So we can still go ahead and do the problem. The thing is, since this is not from a random sample or from a random treatment, whatever findings we get from this problem only applies to these 62 children and these 61 children. We cannot apply it to, all 3 and 4-year-old children who attend preschool or do not attend preschool. So our findings will only apply to this group of people, and that's it. That's mainly what you can conclude with a non-random sample. Number 2, independent. Population 1 is at least 10 times our sample size, and population 2 is at least 10 times that sample size. So population 1 would be all 3, 4-year-olds not in pre-K. And is that greater than or equal to 610? Yeah, we can definitely assume that that is true. Population 2 would be all 3 to 4-year-olds in preschool. Can we assume that is more than 620? And I believe we can assume that is true. Okay, they are talking about specifically, if I jump back here, they were talking about two groups of Michigan children. So we might say, all 3 or 4-year-olds not in preschool in Michigan, and all 3 and 4-year-olds in preschool in Michigan. I would still say those numbers would be true. So since both of these are true, we may calculate a standard error. We may calculate the standard deviation of P1 hat minus P2 hat. That is achievable, which we will have to do later on in the problem. Now, I'm going to clear all this just to get a little bit more room for my normal condition. So if you need to pause and write this down, go ahead and do that. Otherwise, the normal condition is N1 times P1 greater than or equal to 10, is N1 times 1 minus P1 greater than or equal to 10, is N2 times P2 greater than or equal to 10, is N2 times 1 minus P2 greater than or equal to 10. Now, in this problem, we don't know what the population proportion is for either group of children, those that are in preschool or not. So if you don't know what P is, then we mentioned earlier in previous chapters that we can replace it with P hat, and we do know those numbers. Okay, so N1, this is for our control group, there were 61 individuals, and P1 hat is our 49 out of 61. And the reason why I write it like as a fraction is because notice what happens here. So really we have 49 is greater than or equal to 10. Now this N times P, as I mentioned earlier, they may refer to that as quote unquote successes. Well, we had, if you want to consider success being on welfare, which I think would be the exact opposite of what you'd want to consider a success, the number of people that were on welfare is the 49, which means the number of people that were not on welfare out of the 61 should be the leftover 12 from our 49 here. So if you want to check 61 times 1 minus 49 over 61, that should give you 12, which works out. So if you want to do it that way, you certainly can. Now, for our second sample, we had, now let's try it this way. Successes, or basically not being a success here. This should be 38. We should get 38 is greater than or equal to 10. To test that theory, this should be 62 times 38 out of 62. And the 62's cancel, and yeah, we do get that 38. Which means this, our failure people who did not need governmental assistance, should be the leftover people of the 62 from the 38, which would give me, what, 24? Which is greater than or equal to 10. So all of these check out, which means we have an approximately normal distribution. We're good. So all three conditions, well, kind of all three conditions check out. The random condition was iffy, but we decided we're still going to go ahead and do it. But our conclusion can only apply to these children, and that's it. So for our calculations, here's that big, ugly, nasty looking formula. Now just start plugging in numbers. We know what these numbers are. We know what these numbers are, these numbers, these numbers. The only number we don't know at this point is the z. And again, to get the z, you're going to do inverse norm and then the tail area. I mentioned earlier we are doing a 95% confidence interval, which means our tail area is going to be 0.025. So to get that, punch that in your calculator, and you should get 1.96. So this is saying we can add and subtract as much as almost 2 standard deviations away from our mean value here. So here are all the numbers that you should have. And once you do all that, and this is what I'll typically do in my calculations, is I'll figure out what this number is, and then I'll figure out what my margin of error is. Okay, keep in mind, this has been a little while ago. Everything after the plus and minus, all of this is the margin of error. This is how much we may add and subtract away from our point estimate. Okay, so I will always write down what those two numbers are before I get a full, complete last answer. I get that there's a natural 19% difference in my two sample proportions, and all of this, my critical value times my standard error, ends up being with a total margin of error of a little less than 16%. And so finally, if I take my point estimate and add and subtract my margin of error, then I end up with my confidence interval for the difference between these two groups. So we can now take this and write our conclusion. And so we can say that we are 95% confident that the difference in the proportion of preschool and controlled children who needed social services is between about 3.3% and 34.7%. Now, an extra thing that we can now state here is since 0 is not in the confidence interval, and remember, we're trying to see if there's a difference between these two groups of kids. And so since our confidence interval does not contain a 0 difference possibility, then I would conclude that there is a difference in the proportion of preschool and control children who need social services later. So two things here that we're saying. We're saying that they're based on our confidence interval, it definitely looks like the kids that go to preschool have an advantage and that they don't need social services, maybe like welfare or food stamps later in life. Versus kids who did not go to preschool, it appears to be, and we're not saying it's a definite thing, but it appears to be statistically that those kids will more than likely need social services later, more so than kids that went to preschool. Now, the other small thing to conclude here is that since these kids were not randomly selected, then really these results that we found only apply to these 62 kids that actually went to preschool and the 61 kids who did not go to preschool. The only way we can apply this to all 3 and 4 year olds that do or do not go to preschool would be if they were randomly selected from the population. Here is the one problem I want you guys to do on your own, and we will talk about together in class the next day. So good luck, and I will see you next video.